Very good morning. Myself and Dr. Ratu. I am going to present the topic network synthesis of circuit communication network and transmission line. Its code is EC-503. So in the unit third, these are the outline of network synthesis, positive real function LC, RL, RC and RLC, and we cover next topic network synthesis, Foster and core network. After then, we would complete minimum positive real function, then Brun method and both doubling methods, and synthesis coefficient will be discussed. So we will study here one-to-one network synthesis. So question is arises, what is network synthesis? A positive real function, that is PRF, describes the driving point impedance and admittance of positive RLC network, meaning a function is a positive real function if it's physically realizable with resistor, inductor, capacitor and combinations of its like LC, RL and RC. The key properties include being real having poles or zero in the left half plane or on the j omega axis and positive real part for real part is positive. For LC network, poles and zeros alternate on the j omega axis. Here, Fs is equal to m1 plus n1 upon m2 plus n2 multiply m2 minus n2 upon m2 minus n2. Next, network synthesis Foster core network. Foster and core network are fundamental canonical forms of passive network synthesis used to realize a driving point impedance admittance function like an RLC circuit from its mathematical expression. Foster's method uses a partial fraction expansion creating series or parallel structures of simple RLC branches. In contrast, core methods uses continued fraction expansion resulting in ladder-like structure core 1 or core 2 that systematically divide the function, modeling distributed behavior more closely. If we talk about Foster synthesis, that is realized by partial fraction expansion, expands the function Zs cap Z open parenthesis close or y opens close parenthesis by s into a sum of simple terms. Foster 1 realizes Zs a series connected LC tanks and a resistor with capacitor or inductor grouped at opposite ends. If we talk about Foster second, realizes YS is parallel connected AC tanks and resistor with capacitor inductors grouped at opposite ends. We can hear in the Foster form. So inductor and capacitor in first term are in series. After then, inductor and capacitor are in parallel. So this is the structure of LC network in first form, and we find out Zs across this network. If we talk about second form, here L and C, the first terms and first component are connected in parallel. After then, L and C are connected in series. And for synthesis, core synthesis relate continued friction expansion. Method divide the impedance and admittance function into a series of times using long division. If we talk about core first, numerator decrease is higher or equal to the denominator. Involves taking out the higher power terms. In core second, denominator degree is higher or equal to the numerator, involves taking out of the lowest power terms. Now, Brun methods. The Brun word-Dublin synthesis is the converse Vt is equal to Zs The function of Zs is a positive real function, that is, it is a rational function with real coefficient, mapping the right half plane. An algorithm based on Brun multiport synthesis method is presented for the synthesis of blunt element equivalent circuit of linear passive reciprocal multiport, applicable also to noisy multiports. Such multiports are represented by positive real symmetry, impedance, or admittance matrices. Now, word Duffin method. The word Duffin method developed by Reuel Watt and Richard Duffin is a classic technique in electrical network synthesis used to realize any positive real function as the impedance of passive one-port circuit. It works by iteratively applying Richard's theorem to break down a complex impedance function into simpler, realizable components, while foundational, the original method often results in second with. Now, the last topic of unit 30 is synthesis coefficient. A synthesis coefficient refers to numerical value determined during the design process of a system like filters, antennas, or control system to achieve a desired performance, balancing, balancing theoretical goals with practical constraints. It's used in various fields to synthesize a specific function or response, such crafting filter coefficients for digital signal processing or reflection coefficients for antenna array often in polymer. Now, we will teach the topic of unit 4, that is transmission line first, and its outline is transmission line fundamental, lumped parameter equivalent, voltage and current on transmission line, infinite line, characteristic impedance, and propagation constant, waveform distortion, attenuation, phase equalizer, distortionless line. After then, loading, linear reflection on a line, reflection coefficient, input and transfer impedances, open circuit and short circuit line, reflection factors, reflection loss in insertion loss, T and pi equivalent of a line, location of a line fault. After then, construction and design of the two-wire line and coaxial cable will be discussed. So here I will teach you one-to-one topic of unit 4, transmission line fundamental lumped parameter equivalent. A transmission line lumped parameter equivalent model its distributed resistance, inductance, capacitance, and conductance are discrete components in a circuit, typically the T model or pi model, suitable for fundamental frequency 50 megahertz, 50 hertz, and lower frequency where the length is much shorter than the signal's wavelength. So normally in transmission line, they are R, C, G, and L are exist in the transmission line. Now, voltage and current on a transmission line, infinite line characteristic impedance and propagation constant. So these are the formula of Bs is equal to Vr cos hyperbolic Al root y into z. Y means admittance and z is impedance plus root z upon y IR sin L into root yz, and Is is equal to root y upon z Vr sin hyperbolic L into root y into z plus IR cos hyperbolic L into root y into z. So here y is total shunt admittance of the line and z total series impedance of the line. Now infinite line. Question is, what is infinite line? An infinite transmission line is a hypothetical concept of a line with an infinite length that absorbs all incoming signal, resulting into no signal reflection from the end. In practice, a finite line can be made to behave like an infinite one by terminating it with its characteristic impedance Z0, which also prevents reflections. Now, characteristic impedance and propagation constant. The propagation constant, represented by gamma of a transmission line, measures how the wave's amplitude and phase changes as it travels, and it is defined as the square root of the product of series impedance Z and shunt admittance Y per unit length. It is a complex number. Gamma is equal to alpha plus J beta. Here alpha is the attenuation constant and beta is a phase constant. Next, waveform distortion and attenuation. Waveform distortion is a deviation from an ideal pure signal waveform, typically an ideal sine wave in power system caused by unwanted alternations of the signal shape or the relationship between its frequency component. This change, which is usually a degradation of signal, occurs in electrical system, communication channels, and audio processing due to non-linear component and other factors. You can see the diagram. So different waveform with different colors are shown, and it is shown distortion in the wave. And in third diagram, we can see easily here there is a attenuation, the waveform. Phase equalizer. A phase equalizer corrects phase shift in audio signal, preventing phase issues like hazy sounds by ensuring all component all component sorry for disturbance sorry a phase equalizer corrects phase shift into audio signals, preventing phase issues like hazy sounds by ensuring all frequencies arrive at the same time, especially in applications like linear phase equalizer. It can also refer to electrical or power distribution technology that balances power flow between phases in a three-phase circuit, or a more general term for circuit design to correct phase characteristics. It is used historical telephone and video system. Reflection coefficient. The reflection coefficient is a measure of amount of wave that is reflected at an impedance discontinuity. It is also calculated as ratio of amplitude of the reflected wave to amplitude of the incident wave. The reflection coefficient is a parameter that describes how much of wave is reflected by an impedance discontinuity transmission medium. Reflection loss is the reduction power delivered to the load transmission line due to an impedance mismatch between the line and load. When a wave reaches an impedance mismatch, some of the power is reflected back, and this reflected wave in this slide, the last topic of Unit 4 is coaxial cable. It is also taught in Unit 5. A coaxial cable's construction features a central conductor surrounded by a tubular insulating layer, a metallic shield, and an outer protective jacket. This coaxial design places the inner and outer conductor on the same geometric axis, which provides signal shielding from external interference. So we can hear this is the figure of coaxial cable. Next unit is Unit 5. The, the topic of Unit 5 is transmission line second. The remaining topic of the transmission line are taught in Unit 5. So these are the outline. First topic is line at radio frequency. Second topic is parameters of line and coaxial cable at radio frequencies. Next topic is distribution-less line, voltage and current on distribution-less line, extending wave ratio, input impedance, open circuit, short circuit power and impedance measurement on lines, head wave, quarter wave, half wave line. And last, split chart and solution of problem using split chart. So parameter of line and coaxial at frequency. The main parameter of coaxial cable are electrical such as impedance, resistance, capacitance, inductance per unit length, and make detail like the inner and outer conductor diameter, which determine impedance. Other important parameters include its performance characteristic like attenuation, power handling, RF stability, as well as environmental factors such as its temperature range and fluidity resistance. Formulas for coaxial cable calculations Z0 is equal to 138 log 10 capital D upon small d upon epsilon r, and C in picofarad is 7.354 into epsilon r upon log 10 d by d, and inductance in nanohenry is 140.4 multiplied log 10 capital D by small d. Now, distribution-less line. A distribution-less line is a theoretical transmission line where the resistance of the conductor is assumed to be zero. This idealization simplifies analysis by eliminating energy loss to heat, making it a useful model for high frequency applications where resistive losses are of small compared to reactive losses. For distribution-less line, the characteristic impedance is purely real and depends on voltage and current on this line. Now, standing wave. Standing wave, that is SWR, is a measure of impedance mismatch between a transmission line and its load expressed as the ratio of the back voltage to the minimum voltage on the line. In ideal, AWR is indicating a perfect match with no reflected power, while higher values indicate more reflected power, which reduces efficiency and can damage equipment. Standing wave ratio is equal to 1 plus D 1 minus T. D is reflection coefficient. The input impedance of open circuit and short circuit. The impedance of transmission line is measured from terminal of finite length of transmission line. Line length L, load and voltage PR, current IR. PR is equal to ES cos hyperbolic PL minus IS Z0 sin hyperbolic P, and IR is equal to IS cos hyperbolic PL minus PS characteristic impedance sin hyperbolic PL. When line is open circuit, means IR is equal to 0. So we put IR is equal to 0. So Z OC is equal to Z0 port hyperbolic PL. When line is short circuit, that is VR is equal to 0. So in the equation of voltage VR, V equals 0. So ZSC becomes Z0 10 hyperbolic PL. Next slide. Eight wave, quarter wave, and half wave line. An 8 wave line is a transmission line used to match a resistance to a source characteristic impedance, while quarter wave line acts as an impedance inverter to transform impedances. Both are short sections of transmission line used for impedance matching, but the 8 wave line provides directly to match, whereas the quarter wave line inverts. So these are the some formulas are derived on the basis of a 8 wave line, quarter wave, etc. So Z in, if we talk about 8 wave line, so here Z is equal to RR plus JR0 upon R0 plus JRR. The quarter wave line, Z is equal to Z0 square upon ZL. Circle diagram. This diagram shows curve of constant resistance and constant reactance. This may represent either an input impedance or a load impedance. The last topic is Smith chart. A Smith chart is a graphical calculator or nomogram designed for electrical and electronics engineers specializing in radio frequency. A Smith chart is a graphical invented by Phillips Smith used in RF engineering to solve problems related to transmission lines and matching circuit. It visually represents complex impedance and admittance, simplifying calculations for tasks like impedance matching, designing antennas, and analyzing reflections. The Smith chart is a graphical tool for determination of the reflection coefficient and impedance along a transmission line. The Smith chart can help us design matching network and obtain maximum power transfer between source and load. Thank you.